Few science fiction films have done as good a job as Interstellar at making their science feel credible. The spacecraft look functional rather than futuristic. The astronauts speak in terms of real-life challenges: fuel, time, gravity and distance, and even the film's most extraordinary ideas are introduced through calculations, observations, and disagreements over what the available evidence actually means. That attention to detail has earned Interstellar a reputation as one of the most scientifically accurate space films ever made, although that description can be misleading because the film does not treat every part of its story in the same way. Some of what we see is based on well-tested physics, some follows accepted theories into conditions that have never been observed, and some depends on speculative ideas that may be mathematically possible without necessarily existing anywhere in the real universe. The film's black hole, Gargantua, is perhaps the clearest example. Its appearance was calculated using the equations of general relativity, and the way its gravity bends light is grounded in real physics. But the planets orbiting close to it, the extreme passage of time on their surfaces, and the possibility of surviving a journey into the black hole all raise much more difficult questions. The same is true of the wormhole near Saturn, the rotating Endurance spacecraft, the search for habitable planets, the use of cryosleep, and, eventually, the suggestion that gravity could allow information to pass across time. None of these ideas can be judged with a simple label such as accurate or inaccurate, because each rests on a different combination of observation, established theory, mathematical possibility and invention. So in this documentary, my goal is to examine the science of Interstellar one idea at a time, beginning with the future Earth it imagines, and following the journey through the wormhole, across its distant planets and into the environment surrounding Gargantua. Along the way, we will look at what the film gets right, where it stretches accepted physics, which of its ideas remain genuinely open scientific questions, and where established physics ends and imagination begins. By the end of tonight, you should have a clearer answer to the question of how scientifically accurate Interstellar really is, although the most interesting parts may be the ones where the real universe turns out to be every bit as strange as the film. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. The first strange object in Interstellar isn't a ship or a black hole. It's a doorway parked near Saturn, hanging in space where no doorway ought to be. The film calls it a wormhole. Cooper's crew flies into one side and comes out in another galaxy, far beyond any place human beings could reach in time. That shortcut makes the whole mission possible. Without it, the Endurance is still a capable spacecraft, but it has nowhere useful to go. A wormhole isn't something the film invented from nothing. It can appear in the mathematics of general relativity, Einstein's theory of gravity. That theory treats gravity as a change in space-time itself. Matter changes the shape of space-time, and moving objects follow that shape. A folded sheet of paper gives the usual analogy. Mark two dots far apart, then bend the sheet until the dots touch. A short passage between them replaces a long trip across the surface. The paper is only a teaching aid. Real space-time doesn't need to fold through some ordinary room outside the universe. The equations describe the geometry from within. Albert Einstein and Nathan Rosen studied a related bridge in 1935. Their version joined regions of space-time, but it wasn't a safe tunnel for travelers. It closed too quickly, and its structure didn't offer a practical route through. Later work showed that other wormhole geometries could, on paper, remain open long enough to cross. That phrase, on paper, carries a lot of weight. In 1988, physicists Michael Morris and Kip Thorne examined what a traversable wormhole would require. The throat would tend to collapse under gravity. Holding it open seemed to demand exotic matter with an unusual energy condition, often described through negative energy density. Quantum physics can produce small, restricted effects that resemble this. The Casimir effect is one well-known example, but nobody knows how to gather enough of that behavior, shape it into a tunnel, or keep the result stable. Kip Thorne later served as a scientific advisor on Interstellar. So the wormhole was designed to respect a serious relativistic idea. Its round appearance also follows from that geometry. A three-dimensional entrance would look more like a sphere than the flat, glowing ring common in older science fiction. You could see distorted light from the far side wrapped across its surface. That makes the scene scientifically informed. It doesn't make the object available. No known civilization placed the wormhole beside Saturn. No known material can hold its throat open. No experiment has found a traversable wormhole, and no engineering plan tells us how to build one. The film begins by borrowing a solution permitted by certain equations, then placing it exactly where humanity needs it. So the mission's first wonder survives one test but fails another. Relativity can describe the doorway. Known physics cannot yet supply the door. Once the crew passes through it, how much of what happens next still rests on rules we've actually tested? Physics can allow something that nature never actually builds. A bridge may appear in the mathematics and follow every rule on paper, while every known way of making it ends in trouble. You see a simpler version of this with recipes. A recipe can tell you exactly what a meal would taste like if you had the ingredients. That doesn't mean those ingredients are in the kitchen. It doesn't mean they exist anywhere nearby. And it certainly doesn't mean you can keep them stable long enough to serve dinner. Wormholes sit in that awkward gap. In 1935, Albert Einstein and Nathan Rosen studied a solution to general relativity that joined two regions of spacetime. We now call it an Einstein-Rosen bridge. The original bridge wasn't a tunnel anyone could travel through. It closed too quickly, and its shape offered no safe route from one side to the other. Later physicists asked whether a different kind could remain open. In 1988, Michael Morris and Kip Thorne described traversable wormholes in a serious physics paper. Their work turned a science fiction device into a precise research problem. What conditions would a passable wormhole need? How would light behave near it? Could a person cross without being crushed? The equations gave possible answers. They also came with a very large bill. In many models, keeping the throat open requires negative energy density. Ordinary matter carries positive energy. A chair, a cloud, and your body all contribute positive mass and energy. Negative energy would act differently. Quantum physics can produce small effects that look somewhat like this. The Casimir effect is the usual example. Place two conducting plates extremely close together, and the quantum fields between them differ from those outside. Physicists have measured the resulting force. It's real, but it's tiny. A tiny effect between metal plates is a very long way from holding open a tunnel through space-time. We don't know how to collect enough negative energy. We don't know how to arrange it around a wormhole. We also don't know whether the structure would remain stable once matter or light began passing through. Some calculations suggest quantum effects could ruin the passage. Other researchers study special shapes, extra dimensions, or links between gravity and quantum information. These ideas keep producing serious papers because the equations still leave room to investigate. None has produced a doorway that anyone knows how to build. That doesn't make the work pointless. Wormholes give physicists a demanding test for general relativity. They force gravity, causality, and quantum theory into the same problem, where their disagreements become harder to ignore. Even an object that can't be engineered may reveal where our present theories stop fitting together. So the literature keeps wormholes alive in one limited sense. Physicists can define them, calculate their behavior, and debate the conditions they might require. But mathematical permission is not construction. Nature hasn't shown us a traversable wormhole, and physics hasn't given us the materials or method to make one. If the doorway remains an open problem, how firmly can we trust the worlds waiting beyond it? The simplest way to watch a story like this is to keep two ledgers. In one, the wormhole is open and stable because the movie needs a doorway. In the other, everything after the crossing still has to answer to physics. That distinction saves us from two bad habits. We don't have to dismiss every scene because its first step depends on something unbuilt, and we don't have to forgive every later claim because the story began with speculation. One assumption can be granted without giving the whole universe a free pass. You do this with ordinary stories all the time. A detective may have an unlikely reason to enter a locked building. Once inside, though, footprints should still come from feet. Doors should still lead somewhere. Evidence shouldn't change merely because the opening was convenient. We set the unlikely entrance aside. The rest remains open to inspection. So our rule for tonight is simple. We'll allow the crossing as the movie presents it. Then we'll ask what follows from the conditions on the other side. How strong is the gravity? How much energy reaches the travelers? What can their machines measure? What would their bodies endure? This makes the story more interesting, not less. A blanket objection ends the conversation immediately. A bracketed assumption lets us examine each consequence on its own. Some parts may hold up surprisingly well. Others may compress decades into minutes, hide a lethal amount of radiation, or ask matter to behave in ways no experiment supports. The rule also leaves room for uncertainty. Physics can often tell us what a scene would require without telling us whether nature can provide it. That's an important difference. A calculation may say, if these conditions exist, this result follows. It may not say those conditions are common, stable, or even possible outside the equations. We should be equally careful in the other direction. If scientists haven't observed something, that alone doesn't prove it can't exist. Missing evidence limits our confidence. It doesn't automatically close the case. We can sort claims by strength, directly measured, supported by established theory, allowed only under special conditions, or invented for the story. You won't need a degree to follow that sorting. Most of it comes down to asking what the scene assumes, what it shows, and whether those two things fit together. We can enjoy the premise while still checking the bill when it arrives. Because physics always sends one. Gravity costs fuel, time, structure, or human endurance. Radiation deposits energy. Acceleration pushes on tissue. Distance demands speed or patience. Even a fictional doorway doesn't remove those costs after you step through it. So we'll grant the doorway and examine the room beyond. The first expense is waiting there already. What does it physically cost to move people and machines through a place where gravity is doing almost all the work? A larger black hole sounds like the worst place to visit. More mass means more gravity, so the biggest one should tear you apart fastest. That conclusion feels almost unavoidable. It is also wrong in one very important way. You already know the everyday version of the problem. Stand with one foot in shallow water and the other on dry ground. Each foot feels a different condition because they occupy different places. Stretch that difference across your whole body and you can feel a pull, twist, or strain. Near a black hole, gravity can differ from one end of you to the other. Your feet may be pulled more strongly than your head. The same mismatch acts across a spacecraft. One side tries to fall faster than the other. Engineers call these tidal forces. The danger comes from the difference in gravity across distance. Strong gravity alone is not enough. If every part of you accelerates almost equally, you simply fall together. You feel weightless, much as astronauts do while orbiting Earth. Trouble begins when nearby points are pulled by meaningfully different amounts. This is where size plays its little trick. A small black hole packs its mass into a tight region. Close to it, the strength of gravity changes very rapidly with distance. Move a little nearer and the pull rises sharply. That steep change can stretch an object lengthwise while squeezing it from the sides. The unpleasant nickname is spaghettification, and for once the silly word describes the effect rather well. A supermassive black hole behaves differently at its event horizon. Its horizon is much farther from the central mass. Gravity there still prevents anything from escaping once it crosses, but across the length of a person or a ship, the change can be surprisingly mild. So a person could cross the horizon of a sufficiently massive black hole without feeling a sudden local jolt. There is no solid edge to strike, no alarm built into space rings at the crossing. If the black hole is calm and the surroundings are clear, the immediate tidal strain might even be survivable. That does not make the place safe. farther inward, the difference in gravity grows. The same stretching problem returns, and eventually no known material can withstand it. A large black hole delays that fate. It does not cancel it. This distinction matters because the word gravity covers two experiences that feel completely different. There is the shared fall of your whole body. Then there is the uneven pull that tries to take your body apart. The first can be enormous without hurting you at once. The second is what breaks things. Bigger, then, does not automatically mean harsher at the horizon. In a strange reversal, the giant may offer the gentler crossing, but reaching that crossing means moving through everything around the black hole first. So what happens when the danger comes not from the hole itself, but from the hot, fast material surrounding it? A deep hole in the ground can have a gentle path leading into it. A shallow ditch can have a sharp edge that catches your foot. Depth and steepness are related, but they aren't the same thing. Gravity around a black hole works in a similar way. The depth tells you how much energy you'd need to escape. The slope tells you how quickly the pull changes between one place and another. Your body responds to that change. Near a small black hole, the pull can rise very quickly over a short distance. Your feet may be only 6 feet from your head, about 2 meters, but that small gap becomes important. The side closer to the hole falls harder. The difference stretches you. Now make the black hole millions or billions of times more massive. Its gravitational well becomes far deeper. Escaping from close by would take far more energy. Yet the horizon also moves much farther from the center. The same critical boundary now lies across a much larger region. That gives the slope room to flatten. You can feel the basic idea on 2 roads. One road drops 10 feet in 10 feet. That's about 3 meters down across 3 meters forward. The other descends 1,000 feet over many miles, about 300 meters over many kilometers. The second road reaches far lower ground, but each step can feel gentler. A supermassive black hole is more like that long descent. Its total pull is immense, but the change in pull across the length of your body may be modest at the horizon. Your head and feet can fall almost together. For a while, you feel very little stretching. This doesn't mean the giant black hole has weak gravity. It means nearby points experience almost the same gravity. You, your clothes, and anything falling beside you are carried along together. That shared fall can take you across the horizon without an immediate physical signal. No wall strikes you. No sudden jolt marks the boundary. If the black hole is calm and isolated, you may have no local event that says you've crossed it. The size of the black hole sets the scale. For a black hole without spin, the horizon grows in direct proportion to its mass. Double the mass, and the horizon's radius doubles. Your height doesn't double with it. You occupy a smaller fraction of the expanded region, so the tidal difference across you becomes weaker there. This reversal sounds wrong only because everyday gravity trains us to link stronger pull with greater danger. On Earth, those usually arrive together. Near a black hole, the overall depth and the local change can separate. Deeper overall, gentler nearby. Both can be true at once. Farther inside, the slope eventually becomes severe. The gentler crossing has a location, and it doesn't last forever. A large black hole delays the strongest tidal forces until after the horizon. It hasn't removed them. Still, at the horizon of a large enough black hole, the crossing itself may be less violent than standing near many ordinary hazards on Earth. So if the local slope can be gentle while the full gravitational well is enormous, how does that difference reshape the passage of time? Gargantua's enormous mass can sound like decoration, a way to make the black hole feel grand on a cinema screen. But for Miller's planet, that scale is doing real work. Without it, the basic setup falls apart before anyone lands. It's a little like choosing a very wide racetrack. A tight turn forces a car to change direction sharply, make the curve broad enough, and the car can turn more gently. Gargantua's mass makes the curved region around it vast in a way that smaller black holes can't match. That size gives the planet somewhere very unusual to orbit. It can sit deep in the black hole's gravity without facing an immediate tidal disaster. A smaller black hole could still produce strong effects on time near its horizon, but a planet would need to enter a much harsher local slope to reach them. One side would feel a different pull from the other. Rock, ocean, and atmosphere would have a very poor day. This is why the mass isn't just a bigger number, it buys room. Gargantua's horizon spreads across a huge region. Miller's planet can travel close to it without being torn apart at once. The movie needs that room before it can ask harder things about clocks, oceans, or people standing on the surface. Mass alone isn't enough. Gargantua must also spin extremely fast. A spinning black hole pulls nearby spacetime around with it, a process called frame dragging. You can compare it to stirring honey with a spoon. The honey moves around the spoon, carrying anything suspended in it. Spacetime isn't a liquid, but the effect gives nearby motion a preferred direction. Close to Gargantua, that spin changes which paths can remain in orbit. It may let a planet travel deeper than it could around a black hole that doesn't rotate. The mass opens a broad region. The spin helps place Miller's planet within it. Even then, this would be an extreme arrangement. The planet circles near a boundary where stable motion becomes difficult. Small changes in its path could have serious results, and real black holes may be surrounded by hot gas, strong magnetic fields, and dangerous radiation. The film gives Gargantua a calmer setting, allowing the gravity problem to stand mostly on its own. None of this proves Miller's planet would be a refuge or even a place where life could persist. It does something narrower. It prevents the idea from being rejected just because the planet sits near a black hole. Gargantua's size is the admission ticket. It creates enough room for fierce overall gravity and survivable local tides to exist together. Only then does the stranger claim become worth testing. A person on Miller's planet experiences every second normally. Their pulse doesn't drag, their thoughts don't slow inside their own head. Yet someone farther away can see those same seconds add up very differently. How can both clocks work properly while one falls years behind the other? The number Christopher Nolan wanted was not a small difference between two clocks. He wanted 1 hour on Miller's planet to equal 7 years for people waiting far away. That ratio came first, before the physics had fully caught up with it. 1 hour against 7 years means the distant clock gains more than 60,000 hours while the crew gets only 1. Put another way, every second near the planet corresponds to about 17 hours elsewhere. A 10-minute conversation could cost nearly 17 months beyond Gargantua. Nothing would feel unusual to the people talking. Their watches would tick normally. The loss would appear only when their time was compared with someone else's. Kip Thorne did not treat this as ordinary movie license. Nolan had set a condition, and Thorne had to find out whether Einstein's equations could allow it without inventing new physics. The answer could not simply be that black holes slow time, so 7 years sounded close enough. Gravity does slow clocks near a black hole, but nature does not supply any ratio a storyteller happens to request. To reach Nolan's number, Gargantua had to rotate extremely fast. A spinning black hole drags nearby spacetime around with it, an effect called frame dragging. A spoon moving through thick honey gives you a rough starting point. As the spoon turns, it pulls some honey along. Gargantua's spin does something much stranger. It changes which close orbits can exist, and how near a planet might travel without crossing the horizon. That gave Thorne room to place Miller's planet deep in Gargantua's gravity. Down there, its clock could run far more slowly than clocks in distant regions. But the arrangement needed precise tuning. The black hole had to be enormous. Its spin had to sit very close to the physical limit. The planet needed a specific orbit with little freedom to drift. Alter those choices, even while keeping a large black hole, and the 7-year ratio falls away. This also means Miller's planet cannot stand in for what usually happens near any black hole. The scientific work published alongside the film shows that the requested time split can be built under extreme assumptions. It does not turn the planet into an easy or ordinary place. Possible in the equations is a narrower claim than likely in nature. No known planet has been observed in such an arrangement, and the calculation does not tell us that one should exist. The order of events is revealing. Thorne did not begin with a typical black hole and happen to discover a convenient delay. Nolan began with a delay. Thorne then searched for the mass, spin and orbit that could earn it. This was closer to asking an engineer whether a bridge could carry an assigned weight. The answer depended on building almost everything around that demand. The drama supplied the number, and the science found a very narrow path beneath it. So what does a delay that severe do to people living on opposite sides of those clocks? Being near a black hole isn't enough. You could circle one at a comfortable distance and gain very little time. The strange clock effect grows only when the orbit drops deep into warped space-time. Down there, a small change in distance can carry an enormous cost. A spinning black hole changes that terrain. It drags nearby space-time in the same direction as its rotation. Think of a spoon stirring thick syrup. Close to the spoon, the syrup moves with it. Near a fast-spinning black hole, space is pulled around in a similar way. An orbit moving with that flow can survive closer than it could around a black hole that isn't spinning. That closer orbit is the ledge. It isn't a solid shelf, of course. It's a narrow range where the planet's forward motion, the black hole's gravity, and the dragging of space-time all fit together. Only there can its clock run far slower than clocks much farther away. The ledge has to sit extremely close to the black hole. Move the planet outward, and the time difference drops. Move it inward, and a stable circular orbit may no longer exist. The planet could spiral down instead, so the required gain doesn't belong to the whole neighborhood. It belongs to that small strip of possible motion. Ordinary nearby orbits simply don't produce anything close to the required delay. The black hole's spin must also be extreme. A slowly turning black hole leaves its innermost stable orbits too far out. Even a rapidly spinning one may fall short. To place the ledge close enough, the black hole has to rotate near the limit allowed by the equations. That limit exists because a black hole cannot spin faster without bound. Add too much rotation for its mass, and the usual event horizon solution breaks down. Size helps in another way. A supermassive black hole can bend time severely without producing the same violent tidal pull found near a smaller one. Tidal force is simply the difference in gravity across an object. It's what pulls harder on one end than the other. Near a stellar mass black hole, that difference can become fatal long before anyone has time to admire the clock. Near a much larger black hole, that change in gravity can be gentler at the horizon. A planet might avoid being torn apart while still sitting deep in the gravitational field. That sounds generous until you count the conditions: enormous mass, almost maximum spin, the correct direction of orbit, and a position close to the last stable path. Miss any one of them, and the extraordinary delay shrinks or the orbit fails. And there's the cost. The time gain isn't a common gift offered by black holes. It comes from balancing on a thin relativistic ledge beside an object pushed almost to its physical limit. The clock runs slowly because nearly everything around it has been made extreme. A clock can make this place sound almost hospitable. Spend an hour near the black hole, return to find years have passed elsewhere, and the bargain seems astonishing. You have bought time, but the price is living where gravity has turned the surrounding space into a very unfriendly address. First, the planet isn't simply resting beside the black hole. It is racing around it. Think of a car taking a bend far too quickly, except the road is curved space-time and there is no guardrail. The required orbital speed would be a large fraction of the speed of light. Any incoming object, loose gas or grain of dust, would meet the planet with enormous energy. Even something tiny could strike with the force of a much larger impact. Then there is the light. A black hole gives off no light of its own, but material falling around it can become fiercely hot. Gas rubs, compresses, and collides as it spirals inward. That can produce visible light, X-rays, and other radiation. Some black holes also drive jets from the region around them. Those jets are powered by hot matter and magnetic fields outside the horizon. A planet in this neighborhood would need energy from somewhere. Too little and its surface freezes, too much and the atmosphere heats, breaks apart or escapes. Earth gets a fairly steady supply from one distant star. Here, the likely source could be a glowing flow of gas whose brightness changes as material falls in. That's less like living beside a lamp, and more like living beside industrial machinery that sometimes changes speed without asking permission. Life would depend on that machinery remaining active, but not too active. Even light arriving from farther away may not stay gentle. As radiation falls deeper into the black hole's gravity, its frequency rises. An observer near the planet can receive that light shifted toward higher energies. Motion adds another imbalance. Light from the direction the planet is moving toward can look brighter and more energetic. Light from behind can appear dimmer and redder. The sky would not deliver heat evenly. There may also be tides. A supermassive black hole can make the difference in gravity across a planet small enough to avoid immediate destruction. Small enough is doing a lot of work there. Repeated gravitational flexing could still heat the planet from within, rather like bending a wire until it grows warm. How severe that heating becomes depends on the orbit, the planet's structure, and the mass and spin of the black hole. It might provide warmth, or turn the interior into a source of constant volcanic stress. So the slow clock is only the most visible reward. Around it sit radiation, high-speed impacts, uneven heating, and a narrow allowance for orbital error. The planet may gain years elsewhere while losing almost every ordinary condition that makes a world comfortable. And if light itself is bent, shifted, and concentrated on the way in, what would anyone standing there actually see? Gargantua looked wrong to many people when Interstellar arrived in 2014. The bright disk seemed to climb over the black hole, cross above it, and appear below it at the same time. Some people thought the effects team had added glowing rings to make the object look more dramatic. That reaction made sense. Earlier movie black holes were usually dark circles surrounded by flat, bright disks. You could read them at once. Gargantua refused to sit still in that familiar shape because the light around it did not travel along familiar paths. A spoon in a glass of water looks bent because light changes direction as it crosses from air into water. The spoon remains straight. Your view has been rearranged. Near a black hole, gravity does something far more severe. Light from the far side of the hot disk can curve around the black hole and reach you from above or below. You see parts of the disk that should seem hidden. So the band across Gargantua's middle is only the most direct view. The bright arcs around it are also images of that same disk. They have been folded into view by the black hole's gravity. Even the underside can appear overhead. The result feels visually impossible, because ordinary life trains us to expect light to move in nearly straight lines. To build the image, physicist Kip Thorne worked with the effects company Double Negative. Their team traced enormous numbers of light rays through equations describing a spinning black hole. The computer followed each ray backward from a simulated camera to the disk, asking where that light had come from and how gravity had changed its route. The calculations produced features the artists had not expected. Thin layers of the disk appeared wrapped around the black hole. Repeated images gathered near its dark edge, where light could circle before escaping. Those layers were too fine to survive clearly on a cinema screen, but their presence told the team that the strange shape came from the physics. The finished image was adjusted for theatrical clarity. A real disk would have shown a strong brightness difference between material approaching the camera and material receding from it. That effect was reduced because it made the black hole look lopsided and harder to read. The colors and brightness were also chosen for the film. Gargantua was never a raw telescope image. Still, its basic geometry came from bent light. 5 years later, in 2019, the Event Horizon Telescope released the first image of the black hole in galaxy M87. It was blurrier, uneven, and made from radio data rather than visible light. Yet the public had now seen a real dark center surrounded by emission shaped by extreme gravity. Gargantua had looked strange because familiar visual habits were the wrong guide. Once light can wrap around an object, seeing no longer means looking straight at it. So how much of the sky near Gargantua would belong to where it seemed to be? A flat disk around a black hole should look like a bright oval with its far half hidden behind the center. Gargantua doesn't look that way, because the light from the hidden half takes a curved route into view. A simple glass of water can give you a mild version of this trick. A straw looks bent where it enters the water because light changes direction before reaching your eyes. Near a black hole, gravity changes the route far more severely. Light can sweep around the black hole, arrive from above or below, and show you matter that would normally sit out of sight. That's why the disk seems to rise over the top of Gargantua and curl beneath it. You aren't seeing a second disk, you're seeing the far side of the same disk, carried around the black hole by bent light. Part of its upper surface reaches you along one route, another part reaches you along a different route beneath the dark center. So the image contains several viewing angles at once. It's rather like looking at a dinner plate, while a set of warped mirrors reveals its back edge and underside. Except there are no mirrors. Space-time itself guides the light. The dark region also needs a little translation. It isn't a simple outline of the event horizon. The event horizon is the point beyond which light cannot escape, but the darkness we see is larger. Some rays that pass outside the horizon still curve inward and disappear. Others loop around before escaping. Together, those paths produce an enlarged dark area called the black hole's shadow. For a black hole like Gargantua, that shadow appears several times wider than the event horizon itself. So even the black shape at the center is not a direct silhouette. It's a map of which routes end at your eyes and which routes end inside the black hole. Then things become stranger again. A ray can circle part way around the black hole before it reaches you. Another can circle farther. In principle, this creates repeated images of the disk, each one made from light that completed another partial loop. The later images become thinner, dimmer, and packed close to the shadow's edge. You could therefore see the same patch of hot gas more than once. One view arrives by a fairly direct path. Another arrives after swinging around the black hole. A still fainter view has travelled farther and taken longer. They occupy different places in the image, even though they began at the same place in the disk. This means Gargantua isn't showing a single moment from a single direction. It gathers light with different travel times and different histories into one view. The image looks physically impossible only if we expect every ray to come straight toward us. But if several paths can carry the same place into view, which version shows us what is happening there now? An ambulance passing your window gives you a small clue about Gargantua's uneven glow. The siren sounds higher while it comes toward you, then lower once it moves away. Near a black hole, gas moves so fast that this familiar effect changes far more than pitch. It changes the light that reaches us. The gas in Gargantua's disk travels at a large fraction of light speed. One side races toward the camera while the other races away. At those speeds, relativity says the two sides cannot look equally bright. Light from the approaching gas is pushed forward along its direction of travel. Its waves reach us closer together, shifting toward higher frequencies. We also receive more light from that moving material. The approaching side, therefore, appears brighter. On the retreating side, the waves are stretched toward lower frequencies, and less light is directed our way. That side looks dimmer. This is called relativistic Doppler brightening, or relativistic beaming. It's related to the change you hear from that passing ambulance. But the gas around Gargantua moves vastly faster than any ambulance, car, or aircraft. The effect can become strong enough for one half of the disk to glare, while the other looks strangely subdued. Your eyes read this as lighting, but the source itself hasn't been lit unevenly. An artist could make one side brighter with an off-screen lamp. This imbalance has a stricter cause. It follows the direction of the gas. Reverse the disk's rotation, and the bright side should reverse as well. The pattern can be calculated from the speed, angle, and motion of the material. Physicist Kip Thorne worked with the visual effects team at Double Negative to calculate how light should travel around Gargantua. Their rendering showed a strongly lopsided disk. It also produced shifts in color and brightness, that could seem like an accidental lighting error. The finished film softened some of those changes. So the Gargantua on screen is a compromise. It retains enough unevenness for the motion to register, but it doesn't show the full strength of every calculated effect. Even in that softened form, the bright side tells us something important. We aren't looking at a flat ring placed behind a dark circle. We're seeing fast-moving matter whose appearance depends on its direction and speed. That may be the film's clearest scientific win. Gargantua looks unusual because the light has obeyed rules we can test. The bending, repeated views, travel delays, and uneven glow arise from the same relativistic system. Each odd feature has a physical cause. Even the apparent lighting mistake carries information about how the disk is moving. And that brings us to a harder limit. A black hole can be rendered with convincing optics, down to which side of its disk should shine more strongly. But accurate light doesn't make the neighborhood safe. So what would a planet this close to Gargantua need in order to remain habitable? A house can survive an earthquake and still be a terrible place to live. The walls may remain standing while the pipes split, the power fails, and smoke fills the rooms. A planet near Gargantua faces the same distinction. Avoiding immediate destruction only means the walls are still up. Habitability asks much more of a world. It needs conditions that can support liquid water somewhere life could use it. Those conditions must last. The planet needs an atmosphere that stays in place. It needs usable energy and chemistry that can keep working without being repeatedly erased. Most of all, these things have to exist together. Having each one during a different era may do no good at all. That overlap is easy to miss. A planet can pass several tests when we inspect them one at a time. Its orbit may be stable, its surface may avoid being pulled apart, its temperature may enter the range where water could remain liquid. None of those results guarantees a living world. Each result merely allows the next test to begin. You can see the problem in an ordinary kitchen. Flour, water, yeast, and warmth can make bread, but only when they meet in the right amounts and remain together long enough. Drop the yeast into boiling water, or chill the dough every few minutes, and all the ingredients are still there. The process fails anyway. Life also depends on processes continuing through time. Cells repair damage, molecules build, split, and build again. Populations reproduce across many generations. Long before complex life appears, basic chemistry needs a setting that doesn't reset faster than anything can develop. A brief spell of pleasant weather isn't enough if every promising chemical chain soon gets broken. Near a black hole, that continuity becomes difficult to judge. A calm-looking surface tells us very little by itself. Water could be present while the atmosphere is being stripped away. Temperatures could seem tolerable while powerful radiation breaks complex molecules apart. An ocean might remain liquid because intense outside energy is heating it. Yet that same energy could make the surface hostile to life. There's also a difference between being habitable today and remaining habitable. Earth has changed enormously, but its oceans and atmosphere have persisted through long stretches of geological time. That gave life room to adjust, spread, and recover. A planet that swings between mild conditions and repeated catastrophe may never get that room. Each mild interval might look promising to a visiting probe, while the longer record shows one failed beginning after another. So the softer tides around a very large black hole settle only one concern. They tell us a planet might remain physically whole. They don't tell us whether air stays overhead, whether water remains usable, or whether chemistry gets enough uninterrupted time. Surviving the tides is the first filter in a much longer chain. The next filter is harder to see than a stretched ocean or broken crust. What happens when Gargantua's neighborhood begins pouring energy into the planet? A campfire can warm you from across a field, even when the air between you stays cold. Move close enough, though, and that same fire stops being helpful. Near Gargantua, the problem isn't only the black hole, it's everything hot and violent gathered around it. A black hole gives off no light of its own, but gas falling toward one can form a wide, spinning disk. The gas rubs against itself as it spirals inward. That friction heats it to enormous temperatures. An active disk may shine invisible light, ultraviolet and X-rays. Some of that radiation can strike a nearby planet from above, where no ordinary roof offers much protection. Miller's world sits deep inside Gargantua's gravity. That placement creates the clock's split. It can also change the energy arriving there. Light falling deeper into a gravitational field gains energy as measured by a nearby observer. Its wavelength becomes shorter. This is gravitational blue shift, rather like ocean waves arriving closer together as you move toward them. The exact dose on the surface would depend on details we aren't given. How bright is the disk? How thick is the atmosphere? Does the planet have a strong magnetic field? Is dust blocking part of the sky? Those aren't small details. They decide whether the world receives extra warmth or a steady bath of damaging radiation. Ultraviolet light can break apart molecules in the upper atmosphere. X-rays carry still more energy. They can strip electrons from atoms, alter atmospheric chemistry, and help drive gas away over time. A magnetic field can turn aside many charged particles. It can't simply push away X-rays. Thick air can absorb some radiation, but then the upper atmosphere takes the blow and heats up. There may be another source. Matter near a spinning black hole can power narrow jets that travel far beyond the disk. These jets contain fast particles and intense radiation. They don't spray evenly in every direction. They act more like beams. A planet outside the beam may avoid the worst of them. A planet inside one would face an environment far harsher than its temperature alone suggests. We don't know whether Gargantua has such a jet where it points, or how active its disk is. The film gives us a bright disk, but not enough measurements to calculate a reliable surface dose. So there's no firm number to attach to Miller's world. Still, the trade is clear. The deep gravity that lets 1 hour become 7 years doesn't arrive by itself. It places the planet in a region where light can be shifted to higher energy. Hot gas may flood the sky with radiation, and any beam from the black hole could become the least welcome lighthouse in the galaxy. If the planet can endure that incoming energy, what does all of it do to the air and water waiting at the surface? At first glance, Miller's planet seems to have survived the impossible. It circles close to a giant black hole, yet it still has air, liquid water, and a surface you can stand on. The view is astonishing. The real estate is terrible. A habitable planet has to do more than keep water from freezing or boiling. It has to give settlers somewhere to live, build, grow food, and remain for years. Miller's world fails that test before anyone unloads the first supply case. The waves alone would make every ordinary task absurd. You wouldn't build a home beside that ocean. You'd build for an ocean that regularly becomes a moving wall. Foundations would need to resist repeated flooding and crushing impacts. Power systems would have to survive underwater. Landing craft would need a safe surface that may not stay safe for long. Even a sheltered base wouldn't solve the larger problem. The planet's time runs far slower than time outside its orbit. 1 hour on the surface costs 7 years far away. That isn't just strange physics. It breaks settlement as a shared human project. A crew could spend a working day there and return to find that everyone who sent them had grown old. Resupply plans would expire, governments would change, engineers who understood the equipment could be gone. A medical request sent upward might outlive the patient before help could return. And leaving the planet doesn't erase the cost. Any ship descending into that deep gravitational region must climb back out. That takes energy, careful timing, and machines able to work near a black hole. A settlement that depends on regular deliveries would be tied to one of the hardest transport routes anyone could choose. There's another limit hiding in plain sight. A world can possess liquid water without offering usable land, calm weather, healthy soil, or a stable place for machines. Water is one box on a very long checklist. Miller's planet checks it in the most dramatic way possible, then knocks the clipboard into the sea. So the planet isn't a paradise ruined by one unfortunate wave. It's a demonstration of how several impressive features can add up to a bad home. Liquid water draws our attention. The black hole makes the sky unforgettable. Neither fact guarantees that people could remain there safely. That may be the best way to read Miller's world. It isn't an almost Earth waiting for better equipment. It shows that survival depends on the whole setting: air, water, gravity, radiation, terrain, transport, and time all have to cooperate. Once a planet fails several of those tests at once, fascination is no longer enough. You have to sort the dangers by which ones can be managed, which ones demand extraordinary machines, and which ones simply rule the world out. So what should we examine first when a promising planet starts failing the checklist? The first thing to examine is the kind of failure you're facing. A flooded world, a frozen world, and a distant world may all receive the same mark on a checklist. Yet they don't fail for the same reason. That difference decides whether engineers can adapt, whether settlers must wait, or whether no sensible mission should land at all. Miller's world gives one answer. Some environments are hostile in too many connected ways. There may be something familiar, such as water, but the larger setting defeats settlement. The danger isn't one broken part you can replace. It's built into the place. More equipment may reduce one risk while leaving several others untouched. Man's world gives a different answer. Here, the screening process itself fails. The readings seem promising because the person reporting them has changed the evidence. That's an awkward problem for any distant mission. A sensor can measure temperature or pressure. It can't tell you whether a frightened scientist has decided to lie. That makes man's failure partly human. The planet is unsuitable, but the larger lesson sits inside the chain of trust. When a crew is years away, one false report can redirect ships, fuel, equipment, and lives. You'd want independent measurements, repeated checks, and systems that don't depend on one person's judgment. Even then, a desperate person may know those safeguards well enough to work around them. Edmonds offers the third answer. A candidate may survive the early tests without becoming a proven home. The available evidence can point in the right direction, while distance and limited observation leave important gaps. That isn't the same as finding a fatal flaw. It means the case remains open until someone reaches the ground and checks. Miller, Mann, and Edmonds work best as three answers to one settlement problem. Miller asks whether the environment can support people at all. Mann asks whether the evidence can be trusted. Edmonds asks how much uncertainty a mission should accept before committing to a place nobody has examined directly. We make smaller versions of this decision whenever we buy a house. A house can fail because its foundation is cracked. It can fail because the inspection report is false, or it can look sound while a locked room remains unseen. All three may stop the purchase, but each calls for a different response. Repair won't fix fraud. Better paperwork won't hold up a collapsing foundation. And missing information isn't proof that something is wrong. It's a reason to delay the decision until you know more. For settlers, those differences would shape everything. Some risks can be reduced with stronger shelters, extra supplies, or a different landing site. Some require better evidence before departure. Others belong to the planet itself and can't be reduced enough to make settlement sensible. So before choosing the world that looks most like home, how do you tell which failures can be repaired, which demand another inspection, and which should end the mission there? A distress signal seems like strong evidence when someone's life depends on it. It tells you that a person reached the ground, survived the landing, and stayed alive long enough to call for help. That's real information. It just isn't proof that the world around them can support anyone else. Man's planet turns that difference into a trap. The crew doesn't arrive with a full survey. They have readings, a signal, and the reputation of the scientist who sent it. Each piece appears to support the others. The signal suggests survival. The data suggests a possible home. Man's standing makes the data feel safer than it is. You can see the same problem in an ordinary rescue. A voice comes through a radio and says the building is stable. You may trust the voice because the speaker is inside. But perhaps that person has seen only one room. Perhaps the floor beneath them is already moving. Or perhaps they know the building is failing and say otherwise because rescue is their only chance. Thin evidence gives one report too much power. There aren't enough independent measurements to expose a mistake, a blind spot, or a lie. One uncertain claim begins carrying the weight of an entire world. By the time a second source can check it, people may already be on their way. That pressure grows when the crew wants the claim to be true. They have crossed an enormous distance. Their supplies are limited. Earth is running out of time. Under those conditions, a weak positive result can feel more valuable than a strong warning. Hope doesn't have to erase good judgment. It only has to make one doubtful reading seem worth the risk. Man's deception makes the danger obvious, but fraud is only the sharpest version of it. A scientist could report in good faith and still be wrong. Instruments can sample the wrong place. Weather can shift after the last transmission. Ice can hide unstable ground. A few promising chemicals can say little about the air, the seasons, or what happens below the surface. There's another awkward part. A person waking after years alone is also part of the evidence problem. Isolation, fear, and the need to be rescued can change how someone reads uncertain results. Expertise doesn't remove those pressures. Sometimes it gives them more convincing language. The report may still sound precise, while the judgment behind it has begun to bend. That's how a refuge becomes a false positive, long before anyone understands the full environment. The first signs don't need to be worthless. They only need to be incomplete, then treated as final because the mission needs an answer. A true reading from one patch of ground can still produce a dangerously false conclusion about the planet. A distant crew would need more than a hopeful signal. They'd need repeated measurements from different places, independent checks, and enough time to let the planet disagree. They'd also need rules set before arrival, while no frightened survivor is asking them to land. But when every extra test costs food, fuel, and years, how much doubt can a rescue mission afford? Edmonds is the hopeful option. By the time Brand reaches it, the planet looks calm enough to deserve a closer look. There's solid ground, sunlight, and no towering wave racing toward the landing site. After Miller and Mann, that alone feels like a victory. But a better sign isn't the same as a complete answer. Edmonds entered the mission because his world sat in the habitable zone, where temperatures might allow liquid water. That gives you a place worth investigating. It doesn't tell you whether water is present, whether the air is safe, or whether anything can grow there. A house can have a comfortable temperature and still be unlivable. The pipes may be dry, the wiring may be unsafe, the walls may contain something that makes you sick. Temperature clears one condition, it cannot inspect the whole house. A planet works the same way, only with many more ways to fail. Its star may produce dangerous radiation. Its atmosphere may be too thin to hold warmth, or thick enough to trap far too much. The ground may lack accessible nutrients. Liquid water might appear only briefly, or carry chemistry that living cells cannot tolerate. Even gravity can become a problem when people must remain for years. And every answer hides another layer. A breathable atmosphere near the lander says little about weather across a continent. A patch of fertile ground says little about the next growing season. Mild conditions today do not reveal the planet's climate over decades. Edmonds may be the best candidate, and still demand months or years of patient checking. That's the awkward limit of good news. The more promising a world appears, the stronger the urge to stop testing it. Everyone aboard has spent years crossing space. Supplies are finite. Earth is dying. A green light on one instrument can begin to feel like permission from the planet itself, though it's only one reading from one place. Edmonds offers hope because the first filter hasn't rejected it. The world may have the right orbit. It may have tolerable temperatures. It may offer ground where a settlement could begin. Those facts would be valuable. They would also leave most of the survival problem unanswered. So the crew would still need to sample the air, search for reliable water, measure radiation, study the weather, test the soil, and watch how conditions change. They'd need shelters before they knew whether shelters were enough. They'd need crops before they knew which crops could survive. A destination can look better at every step and still fail at the final requirement. And that leaves the mission with a practical problem. No planet can be fully known before people arrive. The first settlement must live inside that uncertainty while it gathers evidence. Its machines must keep working during bad weather, failed harvests, medical emergencies, and discoveries nobody planned for. A promising world only gives them somewhere to try. What kind of vehicle can deliver them there, protect them through the unknown, and remain dependable after years between any hope of repair? Endurance looks like a wheel because the people inside it still have bones, muscles, blood, and an inner ear. Those ordinary human parts become a serious engineering problem when a voyage lasts for years. On Earth, gravity is always asking your body to work. Your legs support you. Your heart pushes blood upward. Even standing in a kitchen gives your bones a small reason to remain strong. Remove that steady pull, and the body starts adapting to a life it was never built to live. Astronauts aboard the International Space Station exercise for hours most days. They run while straps hold them to a treadmill. They pedal a fixed bicycle. They lift against resistance machines that imitate heavy weights. This slows the damage, but it doesn't make weightlessness harmless. Muscles can shrink, bones can lose minerals, fluids move toward the head, balance can feel strange again after landing. A trip lasting several months can accept some of that risk. A mission crossing interstellar space cannot. The crew must arrive able to walk, work, repair equipment, and respond to trouble. Reaching the destination alive would mean little if everyone arrived too weak to build a home. So endurance spins. You've felt the basic effect in a turning car. Your body seems to press toward the outside of the curve. Inside a rotating spacecraft, the floor keeps curving into your feet. That contact can feel like weight. The ship isn't creating gravity in the way a planet does. It's using motion to give the crew a persistent down direction. That choice helps with more than physical health. Beds can stay beds. Water can remain in a cup. Tools can rest on a surface instead of drifting behind a panel. The crew can walk through rooms designed around a floor and ceiling. Human life becomes less like a permanent diving exercise and more like life in a very unusual building. But rotation brings its own limits. A small wheel must turn quickly to produce the same effect as a larger wheel turning slowly. Fast rotation can confuse the inner ear, especially when someone moves their head or climbs toward the center. The pull also changes with distance from the axis. Your feet may feel heavier than your head. No one has yet sent people through years of deep space inside a rotating habitat. Endurance is believable without being a finished answer. Its realism begins with choosing the right human problem, not pretending engineers have already solved every detail. Weightlessness isn't just inconvenient scenery. Over enough time, it can weaken the crew the mission depends on. The wheel shows good engineering judgment before it shows proven engineering. It chooses a problem that cannot be ignored, then offers a physically reasonable way to reduce it. But if the ship must keep spinning for years, what keeps that moving home alive when something inside it breaks? A crew on a long voyage still has to eat, breathe, move, and stay occupied every day. One possible way to reduce that burden sounds familiar from science fiction. Let the travelers sleep through much of the trip. A real torpor would be more than a long nap. The body would run at a lower rate. It would use less oxygen and produce less waste. Food needs might fall as well. The crew would also spend less time awake inside a small, isolated home. On a voyage lasting years, those changes could ease several daily pressures at once. Some animals already do something close to this. A hibernating ground squirrel lowers its body temperature and slows its heart. Bears spend months in a less extreme state while living on stored energy. Human medicine can slow parts of the body's work too. Doctors sometimes cool patients after cardiac arrest. Lower temperatures can reduce the oxygen needed by injured tissue. Those examples don't give us a human hibernation switch. Medical cooling usually lasts hours or days, with doctors watching every change. A deep space crew might need repeated cycles lasting weeks or months. They'd have to wake with their muscles, immune systems, memories, and judgment intact. Waking up groggy is annoying at home. Millions of miles away, it could become a mission problem. That's where the familiar movie version gets awkward. A sleeping body still needs care. Fluids must keep moving. Pressure sores must be prevented. Infection can still happen. Muscles and bones may weaken when a person lies still. Drugs that produce heavy sedation can also affect breathing and circulation. Distance from a hospital does not make any of this kinder. Researchers are looking for ways to lower human metabolism without simply using stronger sedatives. One target is the brain's control of temperature and energy use. Other work studies the chemistry involved in animal hibernation. NASA and the European Space Agency have both examined torpor for long missions. So this isn't a fantasy somebody sketched on a spaceship napkin. It is serious research. It just isn't ordinary mission hardware. Even the possible savings remain uncertain. A crew using less food and oxygen might carry smaller stores. Fewer waking hours could also reduce some strain from isolation and confinement. But torpor would add medical equipment, monitoring, backup power, and people trained to manage it. The ship might save food while taking on something like an intensive care ward. And if one traveler failed to wake normally, the others would face a medical emergency where help could be months away. There's no proven schedule for repeated human torpor, no settled drug plan, and no long record showing that a healthy person can enter and leave it safely again and again. So torpor may one day reduce the human burden of a long voyage. For now, it trades daily needs for medical risks we haven't learnt to control. The crew may sleep, but their survival systems cannot. What happens when the machinery caring for them begins to fail? A ship like Endurance can look calm because most of its problems are hidden behind panels. The crew sees clean walls, soft lights, and one dark silhouette turning against the stars. Behind that surface, thousands of parts are wearing down at different speeds. That changes how we should read the ship. It isn't a machine built around one great invention. It's a stack of unfinished answers that must all work together. Each answer may be plausible on its own. The trouble begins when you connect them. Spin the living section, and the crew gains something close to gravity. But now you need bearings, seals, motors, cables, and joints that survive years of motion. Every moving connection becomes another place where heat, power, air, or data can stop crossing correctly. Put the crew into torpor, and you may reduce food and cabin needs. But the medical system grows more demanding. Sensors must remain accurate, drugs must stay stable, pumps cannot clog, software must notice small changes before they become fatal. The sleeping crew also has fewer hands available when something breaks. Then there's the ordinary work of keeping a closed ship alive. Carbon dioxide has to come out of the air, oxygen has to return, water must be cleaned and used again, waste has to be stored or processed, heat must leave the cabin through radiators because there's no outside air to carry it away. On Earth, a failed pump can be replaced from a warehouse. In deep space, the warehouse is whatever you packed years earlier. You can bring spare parts, but spares add mass. You can bring tools, but repairs need awake people. You can duplicate every vital system, but duplication adds wires, valves, software, and new ways for the systems to interfere. Even dust becomes engineering. Tiny debris moving fast enough can damage a radiator or punch through an outer layer. Radiation slowly harms electronics and living tissue. Shielding helps, but shielding is heavy. Fuel is heavy too. So are batteries, food, water, medical supplies, and every spare motor you hope never to use. This is why the ship's simple shape is a little misleading. The silhouette may be clean, its accounting is not. Every solution sends a bill somewhere else, usually in mass, power, heat, maintenance, or risk. None of this makes Endurance foolish. It makes the design believable. A real interstellar ship probably would not depend on one magical device. It would combine many partial solutions, each carrying a burden the others must absorb. And that may be the most realistic thing about it. The ship doesn't prove we've solved long-distance human travel. It shows what the problem looks like after the engineering has been compressed into one quiet object. But even a ship that carries all those debts still needs a path. What happens when that path approaches the boundary no traveller can cross and return? From a distance, Gargantua seems to have a clear black edge. It looks almost solid, like a dark coin placed in front of all that glowing gas. But that black shape is not a direct view of the event horizon. What you see is the black hole's shadow. Gravity bends the surrounding light, making the darkness look larger than the hole's true boundary. The event horizon sits farther in. A glass of water can make a spoon look bent or displaced. The spoon hasn't moved. Light changed direction before reaching your eyes. Near a black hole, gravity causes a far more severe version of that effect. Light can curve around the hole, travel partway behind it, or miss you entirely. That bending changes the apparent size of the darkness. Some rays that seem aimed toward us are pulled away. Others circle the black hole before escaping. These paths produce a bright, distorted region around a central shadow. So the shadow is an effect made by traveling light. It isn't a surface, and it doesn't show exactly where the event horizon lies. We've seen this effect in real data. In 2019, the Event Horizon Telescope released its image of the black hole in galaxy M87. In 2022, the same network showed Sagittarius A star at the center of our galaxy. Both appeared as dark centers wrapped in uneven rings of radio light. Those famous dark centers were shadows. The telescopes didn't photograph event horizons as though they were cliffs lit from the side. They detected radiation from hot material nearby. Computers then combined observations from radio telescopes spread across Earth, revealing how strong gravity had shaped that radiation. The event horizon itself is stranger and simpler. It is the boundary beyond which every possible path through space-time leads inward. A spacecraft wouldn't strike it. There's no shell, no crust, and no warning line painted across space. For a very large black hole, a traveller crossing the horizon might notice nothing at that exact instant. Local space could feel ordinary enough, at least before stronger tidal forces became fatal. Yet the crossing would still change everything. Afterward, no engine could produce a route back out. Even a beam of light aimed away from the center would continue toward the future inside. To someone watching from far away, the traveller would seem to slow and fade near the horizon. Light leaving the craft would lose energy and arrive later and later. The traveller's own clock wouldn't report an endless pause. It would keep ticking as the boundary passed. So there are two different borders in the same view. One is the enlarged dark shadow that distant observers can measure. The other is the event horizon defined by relativity, hidden inside that shadow and marked by what escape has become: impossible. Once a path crosses that unseen boundary, what does the traveller find on the other side? The first thing the traveller might notice at the horizon is that nothing happens. No impact, no sudden pull against the seat. If the black hole is large enough, crossing the horizon could feel surprisingly ordinary. That sounds wrong, because black holes are famous for stretching things apart. Your feet fall a little harder than your head, and the difference grows as you descend. Near a small black hole, that difference can become severe before you reach the horizon. It can pull a body into a long, thin strand. The cheerful name for this is spaghettification, although the experience would be considerably less cheerful. But the stretching depends on how quickly gravity changes from one part of you to another. Think of standing in ocean water. A small, steep wave can tilt you sharply over a short distance. A broad swell may lift your whole body together, so gently that you barely notice. The total amount of water isn't the deciding factor. The change across your body is. A supermassive black hole has a much larger horizon. For one with millions or billions of times the Sun's mass, that boundary can span millions or billions of miles. Its gravity is enormous. Yet near the horizon, the difference across the length of a human body can be modest. Your head and feet are both falling in almost the same way. So a freely falling traveller could pass through without feeling a special jolt. A small laboratory inside the craft might find no local sign marking the exact instant. Objects would still float. A loose pen wouldn't suddenly drop toward the floor. Your coffee, assuming someone made the questionable choice to bring an open cup, wouldn't announce the crossing either. General relativity says that free fall can feel like weightlessness over a small enough region. This doesn't make the trip safe. Real supermassive black holes may be surrounded by hot gas, radiation, magnetic fields, and debris moving at extreme speeds. Any of those could destroy a spacecraft long before the horizon becomes relevant. But those dangers belong to the black hole's surroundings. They aren't features of the horizon itself. A relatively calm crossing would require a black hole without a lethal feeding environment nearby. And the gentler crossing doesn't last forever. Deeper inside, the difference in gravity grows. The traveler who felt almost nothing at the boundary would eventually face stronger tidal forces with no route back out. Scale changes the order of events. Around a smaller black hole, the stretching may kill you before you cross. Around a supermassive one, you might cross first and meet the worst forces later. The old horror story has much of the physics right, but puts it in the wrong place for every black hole. That leaves a narrow opening for speculation. A traveler might remain intact long enough to make observations after crossing. Those observations could never be reported to anyone outside. Whatever the interior contains, the horizon allows experience to continue inward while cutting that experience off from the rest of the universe. This is where Cooper's fall reaches a hard scientific boundary. He can keep observing after crossing the horizon, at least for a while. But nobody outside can receive what he learns. The horizon isn't a wall he might punch through with a stronger radio. It's a limit built into the shape of space-time. A radio message is carried by light. So is every image and every other signal that could bring information home. Outside the horizon, light can still move away from the black hole. At the horizon, the outward route closes. Inside, every possible route through time leads farther inward. A river gives you a simple way to feel the problem. Suppose you're swimming toward shore while the current carries you toward a waterfall. Far upstream, you can make progress. Closer in, the water matches your fastest stroke. Past that point, swimming toward shore still means moving toward the falls. You haven't forgotten how to swim. The current has changed what your effort can accomplish. The comparison has limits, because space-time isn't water. Still, it catches one important fact. Cooper can shine a light outward after crossing, yet that light cannot increase its distance from the black hole. It moves locally at the speed of light, exactly as physics requires. The geometry simply gives it no path back across the horizon. This blocks more than ordinary communication. Cooper cannot throw out a probe, bounce a signal from something deeper inside, or send a final burst by using more power. Stronger transmitters make brighter signals. They don't create missing routes through space-time. From far away, Romilly and the others would receive Cooper's last signals in an increasingly altered form. The light would lose energy and shift toward redder wavelengths. The gaps between arriving signals would grow. In the simplified outside view, his approach seems to slow near the horizon, but that doesn't mean he remains parked there, waiting to be recovered. In his own time, he crosses and continues inward. That distinction is one of the strongest parts of the film's black hole physics. The person falling and the person watching from outside do not divide events into time in the same way. Both descriptions can belong to the same geometry. Neither gives Cooper a channel back out. And this is the exact point where the scientific credit the movie has earned must stop being transferable. A believable horizon does not make every event beyond it believable. General relativity can describe the crossing, the trapped light, and the one-way future. It does not provide a known method for Cooper to send detailed information into his daughter's room decades earlier. The film now needs him to do more than survive. It needs a connection that reaches a particular person, place, and time outside the black hole. Nothing in the grounded horizon physics supplies that connection. From here, the story begins building one. The first new piece is the Tesseract. Cooper doesn't build it, discover it, or reach it by following any known route through a black hole. He falls from the ordinary geometry of the story into a structure prepared for him. Inside it, different moments in Murph's bedroom appear as places he can move between and touch. That asks much more of physics than the wormhole did. A wormhole is speculative, but it grows from equations physicists already use. General relativity permits geometries that connect distant regions of space-time. We don't know whether a usable wormhole can exist. We certainly don't know how to make one. Still, the starting idea belongs to the same theory that predicts black holes. The tesseract carries a different burden. In mathematics, a tesseract is simply a four-dimensional version of a cube. You can describe one cleanly, just as you can describe shapes in 5 or 10 dimensions. But a mathematical shape isn't automatically a room someone can enter, and an extra dimension in an equation isn't automatically a direction a human can move through. The movie turns time into something like a row of accessible shelves. Cooper can move along those shelves, find selected moments, and affect tiny physical events inside them. That requires a higher dimensional structure with remarkable control. It must preserve him. It must display one bedroom across many years. It must connect his actions to gravity in that room. And it must do all this without letting him simply step into Murph's past. A strong gravity alone doesn't provide those abilities. A black hole can bend paths through space-time. It can slow clocks relative to distant observers. It can trap every future-directed route once the horizon is crossed. None of that creates an archive of chosen moments, arranged for a visitor and fitted with controls. There's no known process by which falling deeper into a black hole would turn its interior into such a carefully organized system. Even the word dimension can make the leap sound smaller than it is. We use time as a coordinate in relativity, so an event needs both a place and a time. But you can't usually walk toward last Tuesday as you'd walk toward a kitchen door. The equations treat space and time as parts of space-time, while still giving time a different physical role. So the tesseract isn't the wormhole's strange little cousin. It's a second borrowed rule, and a much larger one. The wormhole asks whether space-time might contain a shortcut. The tesseract asks whether advanced beings could construct a navigable environment from higher dimensional geometry, place a person inside it, and aim his influence at one narrow thread of history. And even that isn't enough. Cooper must send detailed information, not a vague disturbance. A bookshelf bump won't carry an equation unless each movement can be chosen, repeated, and read. The structure has to connect the right sender to the right receiver at the right moments through a force he can control. That is the standard the ending now has to meet. Relativity does let gravity carry news. If a massive object moves, the change in its gravitational field does not reach everywhere at once. It travels outward at the speed of light. LIGO measured such traveling changes in 2015 when it caught gravitational waves from 2 merging black holes. But that does not make gravity a message service to the past. A radio signal also travels at light speed. That alone does not let you call one chosen person 30 years ago. You still need a route, an address, a transmitter, and some way for the receiver to decode what arrives. Cooper's task demands all of those, with time added to the address. Ordinary relativity gives us no known control panel for that. It describes how matter and energy shape space-time. It also describes how objects move through the resulting geometry. It does allow time to pass at different rates. A fast traveler can return younger than people who stayed home. Someone near a black hole can experience less time than someone farther away. Those effects carry a person forward into other people's future. They do not let that person select an earlier hour and push fresh information into it. Even gravitational waves would not solve this. They move toward the future like light. Producing a readable wave on purpose would also take immense masses undergoing violent acceleration. We cannot tap out delicate binary data by nudging a field with our hands, and no known law lets such a signal stop at one bedroom, ignore every other place and time, then press only the second hand of one watch. The higher dimensional structure is meant to supply that missing access. From Cooper's position, different moments in Murph's room appear available together, almost like rooms along a hallway. Yet, seeing many times from outside is not the same as changing one from inside. A street map can show every house. It cannot choose a doorstep, carry a package there, and make sure the right person opens it. The story therefore needs several extra permissions. Cooper must reach across time. He must target one observer and one set of objects. He must vary gravity with enough precision to encode useful data. Murph must also recognize the signal, preserve it, and extract the intended numbers. And his actions must enter her past without producing contradictions that break the chain leading him there. None of those abilities follows from time dilation, curved spacetime, black holes, or gravitational waves. They require additional machinery and rules. Perhaps a future theory of quantum gravity will alter what physics permits. We do not yet have that theory. Current evidence gives us no working version of this device, nor any tested way to send actionable information backward in time. So the scientific verdict depends on where we draw the line. The film begins with effects that relativity genuinely predicts. Its final exchange uses gravity, but asks gravity to do several jobs the theory has never promised. That difference doesn't make the ending a betrayal. It tells us what kind of bargain the film is making. For most of its running time, it earns our trust with real science. Then, when the plot reaches a locked door, it spends some of that trust on a fictional key. Films do this all the time, though rarely with such expensive physics. A detective story may build its case from careful clues, then rely on one unlikely confession. A medical drama may get every instrument right before inventing a treatment. The earlier accuracy hasn't vanished. It has simply made us more willing to follow the story across one unsupported step. Interstellar earns that willingness patiently. Its black hole has mass, spin, and consequences. Time passes differently near it. Light bends around it. The people who leave Earth pay for distance in years they can't recover. These aren't decorations placed around an ordinary adventure. They shape every decision, which is why the impossible parts arrive with unusual authority. By the final act, the film has trained you to expect strange events that still obey rules. So when Cooper enters the Tesseract, the scene carries the weight of everything that came before it. We've watched relativity produce results that feel impossible while remaining physically sound. The film now asks us to extend that feeling beyond the evidence. That's the clever move. The Tesseract doesn't prove the earlier science was a trick. It borrows credibility from it. The black hole shown on screen came from serious calculations. The backward message did not. Yet they sit close enough together that the boundary can blur, especially when the emotional result feels so satisfying. And it is satisfying. Cooper can finally reach Murph, though not in the way either of them wanted. The watch becomes a bridge between a father who left and a daughter who waited. The equation is completed. Humanity gets a way out. Physics has stopped serving only as a source of delay and loss. For a few minutes, it becomes a way to repair them. That emotional payoff is doing real work. If the scene were only a claim about transmitting data into the past, we would examine it like a lab result. Instead, the scene follows a father trying to keep a promise many decades late. Most people aren't reaching for a red pen at that point. Fair enough. The film knows exactly when our guard is lowest. So the ending should receive neither a free pass nor a scolding for failing to be a physics lecture. Its claim is easier to state. Interstellar uses tested science to build the road, speculative physics to carry it farther, and invention to cross the last gap. Those parts aren't equal, but they belong to the same plot. That distinction is what makes the ending worth judging. The final verdict rests on whether the film lets us tell them apart. The strongest parts of Interstellar are often the ones that refuse to make space comfortable. The film earns its greatest scientific respect when it makes nature harsher than our everyday instincts expect. It gives physics consequences, then makes people live through them. Miller's Planet is the clearest example. The enormous time difference isn't there only to make Cooper miss his children. It follows from general relativity. Close to a rapidly spinning black hole, time can pass far more slowly than it does for people farther away. The exact setup sits near an extreme limit, but the effect itself is real. Einstein's equations demand it. And the film lets that fact hurt. Cooper doesn't return from the planet with a clever story about gravity. He returns to 23 years of messages. That's 23 years for everyone who stayed behind, while he experienced only a few hours. A strange piece of physics becomes birthdays, losses, and ordinary days he couldn't attend. That's unusually good science fiction. It doesn't explain a hard idea and place it back on the shelf. It allows the idea to damage someone. The black hole deserves similar credit. Gargantua isn't shown as a dark ball with a flat glowing ring. Its gravity bends light from the disk around it, that lets us see material that would normally sit behind the hole. The image looks wrong because strong gravity makes familiar sightlines unreliable. In 2019, the Event Horizon Telescope released the first image of a real black hole's shadow. It wasn't a direct match for Gargantua, but the curved light and bright ring belonged to a surprisingly familiar visual family. Scientists had modelled that bending long before the telescope gave us a real object for comparison. The film also respects distance. Spacecraft don't cross the solar system as if the planets share a neighbourhood. Travel consumes time, fuel, food, patience, and human lives. Messages can wait years for someone to return. Hibernation offers some relief, but it also admits the basic problem. People are fragile cargo, and space doesn't provide convenient rest stops. Then there's Dr. Mann. No alien weapon defeats him. Isolation, fear, and the belief that rescue may never come wear him down. He lies because he wants to go home. His failure is painfully human. You may understand the impulse even while watching him turn it into murder. None of this proves that every equation, planet, or survival trick works exactly as shown. It means the film understands something many space stories soften. Nature doesn't owe us a fair schedule. Gravity doesn't care about family milestones. Distance doesn't shrink because someone is brave. A black hole can look beautiful and still be an awful place to need anything. Those choices earn the strongest praise because they resist the easy version. They make the universe less convenient, then force the characters to pay the cost. So where does the film stop following physics and begin asking physics to stretch? The planets and spacecraft sit in a less certain category. They aren't pure fantasy. The film often takes a serious scientific idea and compresses decades of engineering into a machine that already works. Start with the endurance. Its spinning ring gives the crew something like gravity through rotation. You've felt a related effect in a turning car when your body seems pushed toward the outside. Inside a rotating spacecraft, the floor keeps moving beneath you and pushes against your feet that can imitate weight without any magical gravity device. The principle is real. Building the ship is the harder part. A large spinning structure must survive years of stress. It must stay balanced, shield its crew from radiation, and handle failures far from Earth. Even small vibrations could grow into larger problems over time. The Endurance treats all of that as solved. That's fair for a future spacecraft, but it doesn't mean we can build one now. The smaller craft make a similar trade. Rangers move between space and planetary surfaces. Landers carry heavy equipment. Robots handle dangerous work with unusual balance and strength. None of those categories breaks physics. We already build reusable spacecraft, walking machines, autonomous systems and vehicles that dock in orbit. Combining them in one mission with that much reliability is the leap. Then there are the worlds themselves. Miller's planet is covered by shallow water and battered by enormous waves. A water world is possible, and tides near a black hole could be extreme, but a place that close to Gargantua would face more than tall water. Heat, radiation, orbital stability, and the planet's history all become serious concerns. The film gives us the dramatic result while leaving most of that planetary accounting off-screen. Man's planet has frozen clouds and an atmosphere that cannot support human life. Strange clouds aren't automatically impossible. Under different pressures and temperatures, chemicals can freeze or condense in ways that feel completely wrong by Earth standards. We already see unfamiliar weather elsewhere in the solar system. Still, a cloud strong enough to act like solid ground would require very specific conditions. The film doesn't give us enough measurements to know whether those conditions exist. Edmonds' planet may be the most restrained. It has sunlight, solid ground, an atmosphere, and no obvious instant killer. Yet, habitability takes more than air and comfortable gravity. The crew would need safe water and a dependable food system. They'd need protection from local chemistry, disease, and long-term climate changes. They'd also need enough genetic variety, stored knowledge, tools, and replacement parts to begin a population. One promising survey can't settle all of that. That's the pattern in this middle tier. The pieces come from real science and serious engineering. What remains uncertain is whether every piece could work together, on schedule, without one hidden failure ending the mission. So when does that compression become an outright invention? The wormhole is where the movie finally steps beyond known engineering. General relativity allows space-time to bend in ways that resemble shortcuts. Physicists can write equations for such paths, but an equation isn't a construction plan, and no one has ever found a traversable wormhole. Keeping one open may require matter with strange properties, including negative energy in amounts we don't know how to produce. Even then, there's no proof that a spacecraft could pass through safely. The wormhole near Saturn is therefore a doorway allowed by some mathematics, but not confirmed by nature. It belongs to speculation, not current technology. The Tesseract goes farther. Cooper enters a place where different moments in Murph's bedroom appear around him like rooms in a vast structure. He can reach across time through gravity, touch the watch, and send the data she needs. Current science gives us no mechanism for doing this. Higher dimensions do appear in some physical theories. Gravity also shapes time. Those real ideas give the sequence a scientific accent, but they don't make the Tesseract a prediction. Its design, its purpose, and Cooper's ability to use it are fictional. So is the future civilization that places it inside the black hole and closes it when the message is complete. That doesn't make the ending a cheat. It tells us what kind of story we've been watching. The movie begins with crops failing in ordinary fields. It ends inside a structure beyond present physics, yet the distance between those points is paid for at every step. Cooper loses years near Miller's planet. Romilly waits more than 2 decades. Man loses himself to isolation and fear. Murph grows old while her father remains almost the same age. Even the final answer arrives too late to restore the life they might have shared. Progress never comes free here. Every gain costs time, fuel, certainty, trust, or someone's chance to go home. The wormhole offers a route, but it doesn't remove distance. The Tesseract allows a message, but it doesn't return the missing years. Humanity survives, though survival doesn't repair every loss that made it possible. That may be the movie's most scientifically faithful choice. Nature doesn't promise that a solution will be kind. A correct calculation can still arrive after someone has died. A successful mission can save millions and break the people who carried it. Discovery changes what can happen next. It rarely restores what happened before. By the final scene, the science has crossed from established fact, through serious possibility, into invention. The emotional pattern never changes. Each new opening demands a price, and someone has to pay it before anyone else can move forward. So the last answer is both generous and severe. Love guides Cooper toward Murph. But love isn't presented as a new force with equations of its own. It gives him a reason to keep looking, and the Tesseract gives that reason a fictional path. The message reaches her, the species continues. Father and daughter meet once more, separated by nearly an entire lifetime. The future opens, but it opens after the cost has already been paid. Interstellar gives its characters a series of debts, and each one is harder to repay than the last. First comes distance, then time, then gravity. After that comes the problem of getting information back across barriers that physics may not allow us to cross. The film can solve some of those debts with known science. It can only solve others by stepping beyond what anyone has observed. That difference is easy to miss because the whole story looks so convincing. The machines have weight. The spacecraft follow procedures. People make calculations, wait for data, and get frightened when the numbers turn against them. All of that physical detail earns our trust. Then the film spends that trust on ideas that are far less secure. The world near the black hole belongs to the stronger end of the scale. Extreme gravity can change how time passes. A short visit for one traveler can cost years for someone farther away. The exact world shown in the film demands extraordinary conditions, but the mechanism itself comes from Einstein's general theory of relativity. Clocks really do disagree when gravity differs. We've measured smaller versions of that effect on Earth, and our navigation systems have to account for it. The black hole also received more scientific attention than most fictional objects ever get. Physicist Kip Thorne worked with the filmmakers. Equations shaped the way light bends around the spinning black hole. Years later, the Event Horizon Telescope produced the first image of a black hole's shadow. It wasn't Gargantua, and the resemblance doesn't prove every detail in the film. Still, the same gravity stands behind both images. Then the debt grows. Falling into a black hole is one thing. Surviving the trip, entering a constructed space beyond ordinary dimensions, and sending precise messages into the past is something else. Physics contains serious ideas about extra dimensions, wormholes, and unusual structures in space-time. Mathematics can describe more worlds than nature has promised to build. We have no observation showing that a person could use those ideas as the crew does. The same limit applies to the film's final answer about gravity. Our current theories describe gravity extremely well on large scales. Quantum physics describes particles and the other forces with astonishing success. Put both theories into the most extreme places, and they don't fit together cleanly. A black hole hides exactly the conditions where that disagreement becomes unavoidable. So the last scientific debt remains unpaid. We don't yet have a tested theory of quantum gravity. We don't know whether information inside a black hole could ever be recovered in the required form. We don't know whether higher dimensions are physical places, mathematical tools, or something else entirely. That doesn't weaken the parts we do know. It shows where knowledge ends. The film begins with ordinary human limits. Fuel runs low, messages arrive late, parents miss years they can't recover. From there, those limits widen until the story reaches the edge of modern physics. Distance can be crossed, time can stretch, gravity can reshape the path. But every solution carries another cost. And that may be the gentlest way to leave it tonight. Science doesn't promise that every debt can be paid. It gives us a careful account of what has been measured, what the equations permit, and what remains outside our reach. For now, the black hole keeps that final part to itself. The clocks continue at their different rates. Light follows the curved road gravity gives it. And here, far from Gargantua, you can let the unanswered pieces rest. Good night.